So thanks to everybody who posted questions on D2L. We've got 5 questions to go through, covering various different topics. And of course, if you still have questions after this, feel free to send me an email. I'll try to answer as much as I can before the exam on Thursday. So the first question that I've got is asking to explain the sketching of a shear stress on a volume element. And admittedly, this is included in the recommended problems to get you thinking about the visualization of stresses and things like that. But let's just kind of talk briefly about what normal stresses and shear stresses due to the loadings that we've analyzed so far are going to look like. So if I had, let's just say, a rectangular beam like this, and let's say that this area right here is my cross-section face. If I had an internal resultant of a normal force on that cross-section, and we were asked to find or show the stress distribution on a differential element lined up with that cross-section face, we could basically take and place a 3D prism anywhere on that face. And so I'm just going to shade like the face that corresponds with the cross-section itself, and any of those, if I were to blow it up and show it a little bit larger scale, what I would have to show for the stresses would be simply a normal stress on either face. So anywhere that we go on that cross-section face, the normal stress is going to be in the longitudinal direction, the same direction as n, and not n, this will be sigma, and sigma is also going in the same direction as n on the cross-section face itself. So on the cross-section face, sigma is pointed out of the face, meaning it's in tension, and the normal force that we showed is also in tension. Now, if I had a bending moment, that's a little bit different. So if I had a bending moment applied here, let's say I've got a bending moment like this, where there's compression on the top, tension on the bottom, and I'm just going to go ahead and show like the neutral axis here as well too. Let's say we're asked to show the stress distribution for differential elements at the top, at the neutral axis, and at the bottom of this cross section. So here is a differential element at the top, and I'm just going to shade the face that's lined up with the cross section cut itself. Here's one that's lined up with the neutral axis, and then down at the bottom we've got one lined up with the cross section as well too. Same kind of an idea. At the top, our differential element is going to be undergoing compression, and that stress, compression means it's going to be pushing in to the face, normal stress on either side. If we were to look at the stress distribution for an element at the neutral axis, like right here, because this is the neutral axis, is not undergoing any normal stress due to the bending moment, so I would just leave that blank. And then down at the bottom, visualizing this element right here, it is going to be in tension at the bottom, so I'll show it this way with the arrows pointed out of the elements. And if I wanted to put a number on these, I could calculate what it is and say 10 KSI or 5 KSI, whatever you want. But this is just trying to get you thinking about how does the stress vary with the location on the cross section. Another way that we do this is that if I were to look at like the side of this beam, if this is my cross section right here, and I've got a moment applied to it this way, we often show like the variation of stresses just with a two-dimensional plot like this, where I have all compressive stresses at the top linearly varying down to the neutral axis, which is right here. At the bottom, I have increasing linearly normal stresses in tension on the bottom. So this kind of plot is showing it continuously. These kind of plots on the left are really showing them for individual discrete elements. Either way, is totally fine from visualization standpoint. Now, with respect to torsion, it's the same exact idea, but now we're talking about a shear stress due to an internal torque. So if I were to draw an internal torque like this, I can also draw it this way, and I think that's helpful for this type of exercise. If I was interested in what the stress profile is for an element oriented at the top, or maybe an element oriented here on the left hand side, let's look at each of those elements individually. So this one here, this is the cross-section face itself. The top of it, this top, that's the outside surface of the shaft itself. Here, for the element on the left-hand side, I do the same thing. I draw my differential element. This is the cross-section face itself, and then the outside is this face on the left, the lower left. And so the question is, we know that a torque causes a shear stress, but I want you to be able to visualize like what direction is that shear stress going. So if we call this point up at the top A and this other one B, if we're looking at element A has a shear stress on this cross-section face somewhere. The question is, what direction is it going? And the touchstone for that would be, what direction is the torque, the internal torque on that cross-section going? Here it's going counterclockwise, and so I need to draw a shear on the face that is also going in that same counterclockwise direction. It's like the center of the shaft is down here, and so it's causing a counterclockwise rotation about the center of the shaft. And then because of the complementary property of shear, we also have shear stresses going in this direction as well too. The same thing happens at point B, like the center of the shaft is over here, so to continue that counterclockwise rotation, it's going in the same direction as the torque itself. And then due to the complementary property of shear stress, I show it on this other face in the longitudinal direction as well too. Now there's two other faces that I haven't shown here that also have shear stresses on them, but for this view of this element, that's kind of the best that we can do. Okay, so hopefully that answers your question about how do we diagram the stresses on an element. And so we talked about normal stresses due to a normal force, normal stresses due to a moment, and then I think what your question was really about was, how do we visualize the shear stress on an element for torque in a circular shaft? Next question we've got, the shape of shear and moment diagrams, concave versus linear. So Everett says, when using this graphical method, I'm slightly confused as to when to use a parabolic or a linear shape when connecting two values on the shear graph. For example, in question 645, we use a graphical method and do not calculate the functions. The shear function in the solution is concave down as opposed to linear between points A and B. So what Everett's talking about is this point here, A, this point here, B. The question is, why is it parabolic and specifically concave down as opposed to linear? And so it's all about and I think we get a note from Everett that he figures it out because of the triangular increasing distributed load, and he's got it exactly right. And this is where, there's two different things that you could do. One is that you can always figure out what the equation of the shear is between A and B. And then based off kind of Calc 1, Calc 2, you can figure out, is it concave up, concave down? That'll always work. You could even plot out a couple different points if you wanted to and figure out what the curvature is, and that'll always work. So getting the function, if you're not sure about it, and then plotting it out, or just looking at the signs of like the x squared value, things like that, and trying to figure out is it concave up or concave down, that'll always work. The other graphical method that's out of 6.1 in your textbook tells us that the slope of the shear at any point is equal to the intensity of the distributed load at the same point. With that in mind, the way that I can figure out that the slope at A initially is horizontal, or in other words zero slope, is to look at the distributed load value at that same point. So if I go up to the loading diagram at point A, which is right here, the height of this triangle, of this linearly increasing distributed load, is 0. So here W equals 0, and then over here on the far right hand side, W equals negative 3 kilonewtons per meter. That tells me at A, the slope of the shear diagram is 0. At B, the slope of the shear diagram is some negative value. So one thing that's helpful, I think, is once you've plotted your points, which I'll show here with like little circles. So I know the value of A, at A, I know the value at B, and then based off the loading diagram, you can also put in what the slope is going to look like. So that's usually how I draw these. I draw the value using a point, I draw a line showing what the slope is going to look like, and then I can clearly see, in order to get from A to B, there needs to be some downwards curvature. So another way to think about it is linear in shear means parabolic in linear in loading, which is what we have up top of the triangular load. Linear in loading means parabolic in shear, means cubic in moment. And then figuring out concave up, concave down is a matter of looking at what is the value of the diagram above at that same point. That'll give you the slope. Okay, so hopefully that answers Everett's question about parabolic versus linear. It's all about the calculus-based rate of change relationship between distributed load and shear and moment, and that'll help you kind of figure that out. Alright, question 3. So Abdullah is asking, can you please explain how you drew the diagrams in problems 559 and 561? Okay, so that is this problem here, and I've also printed out the recommended problem solution for 561 as well. So let's talk about that. So basically there's two different ways to go about it, just like with axial members and just like with beams. It's all about either free body diagrams in equilibrium or the graphical method. And so that's kind of what I note right here. You can determine the internal torque either by creating section cuts with free body diagrams and using equilibrium, or using the graphical method that we've talked about before. So step number 1 is going to be going from the loading diagram that you see right here in 3D down to like a 2-dimensional representation. And so this is where we use the right-hand rule. And so we use the right-hand rule, and that's critical because it tells us that the direction of the moment vector, the torque vector at point B that's being applied, is to the right. And it tells us that the direction of the torque vector, the applied torque vector at C, is to the left. And I get that just by using the right-hand rule for these rotations that we see right here. Now once we've gotten to that, there's two different ways to go about figuring out the internal torque diagram. So the more robust method would be, if I want to know the torque between A and B, I make a section cut and then I make a free body diagram. So for between A and B, I have a section cut like that. I always draw my internal torque, which I don't know yet, pointed away from the section cut. So that's torque AB. Free body diagram should include a coordinate system as well too. And then now when I sum the moments about the x direction equal to 0, I just get torque AB. So torque AB has to be equal to 0. And that's just clear from the free body diagram in equilibrium. Now if I make a section cut between B and C, then I'm going to get unknown torque BC on the section cut, but I also have to the left of the section cut this 60 pound-feet pointed to the right. So that's 60 pound-feet. And if I do the same exact equilibrium equation, sum the moments about the x-axis equal to 0, I get now 60 pound-feet plus TBC. In other words, TBC has to be equal to negative 60 pound-feet. And so on and so forth. Just there's one more section left, CD, and I can clearly see that that's going to be equal to 0. So the equilibrium free body diagram method is the most kind of comprehensive, the best way to get partial credit, but often kind of a slower way to go about diagrams like this. So what you can do as an alternative, If you're comfortable with the the free body diagram equilibrium method, is then you can go to the shortcut, the kind of the graphical method that simply says every time that we have, as we go from left to right across a beam, we start out at 0, and then anytime I have an applied torque pointed to the right, it will make my internal torque jump down whatever the amount of that applied torque is. So here I start at 0, there's no applied loads between A and B, and so it stays at 0. As soon as I get to B, I have an externally applied torque of 60 pound-feet to the right, which means that I drop down 60. So I start out at 0, I drop down 60, now I'm at negative 60. Same thing, nothing happens between B and C, and so I stay at negative 60, and then as soon as I see an applied torque pointed to the left, it makes my internal torque diagram jump up, so I go from negative 60 plus 60 to 0, and then nothing happens between C and D. So that's how we do it graphically. Now, graphically doesn't help if I'm trying to get a function for the torque, but for relatively simple loadings, it works just fine. Now, for 561, this is where it gets a bit trickier, and so it's the same idea. We have to go from the loading diagram that's provided in 3D, and then I change that into a two-dimensional kind of global free body diagram, and here you see the 1,000 Newton meters per meter. That's the applied distributed torque between C and B, and that's what you see right here. I've represented it as a rectangle to recognize that it's a constant uniform torque. Same thing over here. 500 Newton meters per meter. They had an issue with the units, and I made a note of that. But same thing, it's a constant uniform distributed torque, and I've shown the direction of the arrows, and I've shown a rectangle recognizing like the area underneath that, because that's how we get the resultants. And then it's the same idea. I have the free body diagrams shown right here for the section cuts, and that's how I get to these internal torque equations right here. And again, it's all about whenever you make a section cut, so like for example the section cut between C and B, here's the free body diagram for that. I show my internal torque pointed away from the section cut, and then if you're keeping everything to the right of the section cut, you got to be really careful about making sure your distances are correct. And so the other way to look at this, like the graphical method, would simply say, look, the slope of the torque diagram is equal to the intensity of the distributed torque. So here, the slope of this line right here should be 500 Newton meters per meter, and the slope of this line over here should be the negative 1,000 Newton meters per meter. So those are the two different ways to go about it, but I think that for a problem like this, getting the equation and using, you know, free body diagram equilibrium approach is definitely the best way to go about it. Then once you have these equations, you can simply plot it out, because this is the x direction, this is your, you know, positive torque direction right here. You can just plot these two equations right here, no problem at all. So hopefully that answers Abdullah's question about how to create the diagrams for 559 and 561. Okay, question 4. So this is from Max, and he says, can you explain how to know where the neutral axis of a shape is? And so, in a nutshell, it's at the centroid of the shape. And so, the only real exception is when you have a a cross-section with multiple materials. But pretty much all the ones that we're going to be dealing with, 95% of them, I'm just going to draw a few different section shapes here. We'll even do that, and maybe an I-beam as well too. So when we talk about the neutral axis, what we're really saying is the neutral axis is the axis at which point there is no strain due to a bending moment. And with these, the neutral axis is basically specific to a moment. So here, if I have a horizontal moment and if I had a vertical moment, I would actually have kind of two different neutral axes that I'd have to look at kind of individually. But let's just break it down one by one. So here, if I have a moment acting horizontally, I need to figure out where the location of the neutral axis is. Now, the moment itself is applied at the neutral axis is one way to think about it, but don't worry too much about where the moment is applied. The moment is applied in a direction, and then we use the neutral axis to figure out how it spreads the stresses across the cross section. But fundamentally, the overall centroid of this shape, so that's the top flange and the web as well too, this horizontal piece and this vertical piece, the centroid of all of those elements together combined is where the neutral axis passes through. Now, if I had another moment applied, you know, to this shape as well, I would also have another neutral axis to deal with, but it also passes right through the centroid vertically. And so the z-axis is just another word for the neutral axis parallel to the you know, in that direction, and the y-axis you can also think of as a neutral axis. The reason that they're not completely interchangeable is that when you have two moments applied at the same time, the neutral axis actually is some combination of the two directions depending on how strong each of the moments are. So this would be like the composite neutral axis, but we just keep them separate. We don't do a lot of work trying to figure out what the angle of the true neutral axis is that combines bending about both axes. I want you just thinking about neutral axis in terms of z and y, and those pass right through the overall geometric center of the shape. And so another way to think about that is, you know, in some of the examples we call this distance like y bar. You could call this distance here like x bar if you wanted to. Those are just measured from arbitrary locations, but it is passing, those axes passing through the centroid of a shape. So the way that we find that, for example, like y bar has that equation. It's the first moment of area of each of the individual shapes divided by the summation of the area of all the shapes. So if the top flange here is shape 1 and the bottom flange here is shape 2, each of those have their own individual centroid with their own distances to the centroids. So this is like y tilde 2, this is like y tilde 1, and then we just use this equation to find, like, for example, the distance from the bottom of the shape to find where the neutral axis is. All of these other shapes, I mean, pretty simple to figure out where the neutral axis is, and we traditionally measure the distance from the bottom of the shape to the neutral axis, but you could measure it from the top, you could measure it wherever else you want. And so all of these are relatively simple to find the location of the centroids. And then, you know, some shapes like this, like the eye shape that I wanted to show you, just like the rectangle or the circle, if it's a doubly symmetric shape like this eye shape, if the geometry on the top is the same as the geometry on the bottom in terms of thicknesses, distances, stuff like that. If it's doubly symmetric, then you can also make the assumption that the centroid is just simply half the height, half the width, whatever else you want to call it, b over 2 maybe. There are plenty of shortcuts, and keep in mind that in your exam formula packet here, it shows you the location of the centroid for most common shapes. So that's a good resource in that regard as well too. So hopefully that answers Max's question about how do you know where the neutral axis of a shape is. I want you to be able to find the centroid of a shape and then assume that the neutral axis is passing through it. The one exception that we want to talk about is the composite beams. So we had the example where we had like aluminum on the top and steel on the bottom, and then we either transform that into all aluminum, which would look like this. I'll call the bottom like AL prime. It's now aluminum, but it's mimicking steel. Or this would turn into a cross section of all steel, where the bottom stays as steel and then the top gets really narrow, and I'll call that steel prime. Either of these transform beams is what you would use to find the location of the centroid. So these will have a centroid, and that is where the neutral axis is. It's not the center of the original shape, because all that we were looking at is just geometry, and it's not the geometric center of that shape because the stiffness of the aluminum and the steel are different. So we have to use the transform section and find the centroid of the transform section in order to find the neutral axis. So that's one difference, where it's not purely the geometric center. It really has to do with the center of stiffness is really what we care about. And I would point out that the distance for either of these, like the y bar value for either of these transform beams, will be exactly the same. It doesn't matter if you change it all aluminum or all steel. The distance to the centroid from the bottom will be the same. Okay, linear normal stress distribution. So Max also asks, how do we find the slope of a linear stress or strain distribution on a differential element on a beam or some material exposed to a bending moment? Okay, so I don't know if I understand precisely what the question is, but I think I'll try to answer it as clearly as I can. So potentially what Max is asking is, if we had, let's look at like the side of a beam here, and then like this is a section cut, and let's say that I've got a bending moment applied to it. He might be asking, if I want to plot out the strain and if I want to plot out the stress, how do I figure out what like this slope is right here, or what this slope is right here? And if that's the case, it's all about calculating, well, you know where the neutral axis is, and that's where this passes through 0. And so in order to figure out the slope, really all that you would need to calculate is either what is the maximum like stress on the top, or what is the maximum stress on the bottom. Same thing with the stress. If I knew what this distance was, sigma max compression, or if I knew what this distance was, sigma max tension, because this is all tension on the bottom here, this is all compression at the top here. If I knew what the width of that triangle was, then I would be, and I knew what this height is here, and that would just be the distance from the bottom of the section to the neutral axis. If I knew what that was, this would be like y bar, then I could easily calculate what the slope is. Now, when he says differential element, I don't know if he means, well, what if we were looking at like this little piece right here, and that would simply be a matter of, you know, if you know what the slope is of any of these diagrams, it is multiplying times the distance to, you know, that differential element. So if you knew what the slope was and you knew what your, well, let's call it y value is, you just do y times whatever the slope is, and then you could calculate for a given point what that stress is going to be on that differential element. So hopefully that's what Max was asking about. If not, he can let me know. But it's all about calculating the stress at, like, say, the extreme fiber, knowing where your neutral axis is, and then knowing what those heights are to the top or to the bottom, and that'll allow you to calculate the stress slope, no problem at all. Okay, so that's all the questions that I had submitted. Again, like I said, feel free to submit more questions either to me via email. You know, I'll try to answer as many as I can. We'll see if school is open tomorrow or not. I'm going to have limited availability, but if you want to try to meet up, you can always send me an email and propose some times, and I'll try to meet up as much as possible. Definitely the biggest bang for your buck is going to be those recommended problems. So I would definitely focus on those the most. And other than that, you know, good luck, stay safe, and I'll see everybody on Thursday at 10 o'clock for the next exam. Good luck with your studying.